We're going to begin our study of chemical equilibrium. And chemical equilibrium deals with figuring out how far a chemical reaction goes toward product. Last chapter, we dealt with how fast chemical reactions go. In this chapter, we start thinking about how far they go. So imagine we have this particular chemical reaction where dissolved calcium ion reacts with carbon dioxide gas and liquid water. And it forms solid calcium carbonate and two dissolved protons. Now what's interesting about this reaction, and all reactions in principle, is that they're reversible. So while this reaction of course proceeds to form the solid calcium carbonate and protons, it's also the case that the calcium carbonate solid formed and the protons formed can react and reform your reactants. So how do we tell which of these two reactions is happening more quickly, the one in the forward direction or the one in the reverse direction? Well, what we do is we could set up a system where we were monitoring the concentration of calcium ion in units of molarity with time. And if we were to see the concentration of calcium ion grow as the reaction proceeded, of course it would slow down as time went on, we'd be able to say, all right, the concentration of calcium ion is getting larger. That must mean this isn't happening to a greater extent because this means it's losing calcium ion. This would mean that this reaction is happening to a faster extent. So this would represent the case where the reverse reaction was going more quickly than the forward reaction. And of course, the opposite could potentially happen depending on how we set up the conditions. If we were monitoring the calcium ion concentration with time and we saw this, we would know that in this case, the forward rate of the reaction would be greater than the reverse rate. But in each case, we would see this effect, of course, as the reaction proceeds. And in this case, these reactants are being consumed, the reaction slows down and ultimately levels off at some particular calcium concentration, which would be here on this graph. In this case, the reaction slows down as these are consumed, and that levels off at some particular spot, and that would be this calcium concentration. And these would be what we call the equilibrium concentrations of calcium. In experiment 1, this would be your equilibrium calcium concentration. In experiment 2, this would be your equilibrium calcium concentration. And it should make sense that at equilibrium, when you reach this point where the calcium concentration is not changing and therefore nothing else is changing, it would be the case that the rate of the forward reaction is going to equal the rate of the reverse reaction. You can't have one of these being faster than the other, because if so, you'd have the buildup of something and the decay of other things. So this is a key point with equilibrium. At equilibrium, we know the rate of the forward reaction equals the rate of the reverse reaction, and therefore at equilibrium, the concentrations of everything level off. Now, what's really interesting about reactions at equilibrium is that we can set up some mathematical relationships between reactants and products based on the stoichiometric ratios of reactants and products. So we're going to just do some really simple examples here to show how this works. It's very useful tools here. So let's say I have some reactant A going to a product P in this fashion and in this stoichiometric ratio, where 1R reactant changes to 1P, one product molecule. If we do that, we know that at equilibrium, so this is a capital K, there's going to be a particular ratio of product raised to its stoichiometric power and reactants raised to their stoichiometric powers. So it works like this. You take the products and raise them to their stoichiometric power, which in this case is 1, And you take the reactant and put those on the denominator and raise those to their stoichiometric power, which of course is 1. These concentrations in this ratio is going to equal a particular number at equilibrium. And this is always going to work. Of course, this has to be this value has to be measured experimentally, but that's going to be true for this reaction at a particular temperature. Now let's say we had a different chemical equation. In this case, we'll say we have 2 reactant molecules reacting to combine and form 1 product molecule. If that was the case, the equilibrium constant expression for this reaction would look like the following. The concentration of the product molecule on the numerator raised to its stoichiometric power, which is 1. I'm just not going to put the 1 in there. And then we'll divide that by the concentration of the reactant molecules raised to its stoichiometric power. So the equilibrium constant expression would be some equilibrium constant value would be equal to the concentration of the products divided by the concentration of the reactants squared. So we can apply this to a real chemical reaction. We'll take copper 2 ion reacting with 4 molecules of ammonia, all in the aqueous phase, and this can react reversibly to form what's known as a tetraammonium copper 2 complex. And if we were going to write the equilibrium constant expression for this particular reaction, we'd write the concentration of this complex, which is just one of them. So we'd write it like this. We wouldn't raise it to any power because there's just one of them. We divide it by the concentration of the reactants raised to their respective stoichiometric powers, and it would look something like this. Now there's some things to keep in mind when doing this, when writing equilibrium constant expression. The first thing that you're going to want to recognize is you do not include solids and liquids. So solids and liquids are not included in the equilibrium expression constants. We keep those out. And that's because these concentrations do not change. However, we will include aqueous and gaseous substances will be included. And you can see that I did indeed include all aqueous phase. I should have wrote it in here. Sorry about that. All aqueous phase substances are included in the equilibrium constant expression. So let's do this for a few examples. I'm going to write out a chemical equation here. So let's say we have H2 gas plus I2 gas going to 2HI in the gas phase. What would the equilibrium constant expression be for this particular reaction? Well, let's see. The equilibrium constant, if we use concentrations, so I'm going to write Kc, would be the concentration of my product squared divided by the concentration of hydrogen gas and also divided by the concentration of iodine. Notice there's no stoichiometric coefficients here, so these are just both to the first power. If we use gases as pressures, if we use pressure instead of concentration, we write Kp. And in this case, we write it as the pressure of Hi squared divided by whatever the pressure of hydrogen gas is, and also divided by whatever the pressure of iodine is. Now there's a relationship between these two that's always going to result anytime that we have gases in the equilibrium, we have gases in the chemical equation. There may be a difference between Kc and Kp, and we can see that in the following way. If we use the ideal gas law, we know that pressure is nRT over V. Well, N over V, that's moles per liter, which is concentration and molarity, which is what we use in these expressions. So that would mean that the pressure of HI is going to be the concentration of HI times RT. So I can plug this in for all these values here, and we can check out and see what the relationship between the two are. And it would work like this. Kp would be the concentration of HI times RT. For one of these, I have to do it for the other as well. Concentration of HI times RT. So the numerator now is PHI squared, right? Because if I square this, this is squared and that's squared. So I've written that on the numerator. And then on the denominator, we just write the concentration of H2 times RT, just to the first power, and the concentration of I2 times RT. In this particular case, all of the RTs on numerator and denominator cancel. RT cancels RT, RT cancels RT, and we see that in this case, Kp is going to be HI squared divided by H2 and also divided by I2. So in this case, Kc and Kp are equal, and that will be the case when you have the same number of moles of gas on both sides of the equation. So notice I have 2 moles of HI, which gives me 2 moles of gas on this side, and I have a mole of HI and a mole of H2 and a mole of I2 on this side for 2 moles. So in the case where you have equal amounts of moles of gases on both sides, Kc and Kp will be equal. There are some cases where that will not happen. All right, let's try another one. Here's this particular problem. We're going to write the equilibrium constant expression for calcium carbonate dissolving, not dissolving, but this would happen if you're heating it. This happens in the forward direction. You get calcium oxide and you get carbon dioxide gas. Now, how would one write the Kc for this particular reaction? Well, Kc for this particular reaction, that's going to be the concentration of carbon dioxide, and that's it. We don't include solids in the equilibrium constant expression. Kp for this particular reaction would be equal to the pressure of carbon dioxide, and that's it. There's nothing else that we include in this particular chemical reaction. Now, if we wanted to see the relationship between Kp and Kc, we do this trick again, where we recognize that pressure is nRT over V, which is the same thing as the concentration, in this case of CO2, times RT, right? This is concentration. And so the pressure of carbon dioxide is CO2 times RT. So for this case, Kc is the concentration of CO2. Of course, Kp is the pressure of CO2, but we've just shown here that that's going to be equal to the concentration of CO2 times RT. So in this case, we have a difference in the number of moles on the product side than on the reactant side. There's 1. And we also see there's a difference between Kc and Kp, right? Kc is simply the concentration of CO2, whereas Kp is the concentration of CO2 multiplied by RT. All right, let's try one more. We'll do one more. Last one. Calcium ion dissolved in water plus 2 bicarbonate ions dissolved in water reversibly reacts to form solid calcium carbonate and CO2 gas and liquid water. What is Kc for this particular reaction? And what is Kp for this particular chemical reaction? Well, Kc is just going to be the concentration of the products, concentration of CO2 raised to their stoichiometric powers. Notice I'm not including calcium carbonate or liquid water because liquids and solids do not belong. And we're going to divide that by the concentrations of the aqueous species in the reactant side raised to their stoichiometric power. So don't forget to raise the bicarbonate to the second power. For Kp, we do the same thing, but for any gases that we see, which we see over here, we put them in pressure form. So I put PCO2 over here, and the denominator is going to be the same. Of course, we're not going to express aqueous concentrations as pressure. So this would be how we would write the Kc expression for this chemical reaction, and this would be how we write the Kp expression for this chemical reaction.